You have x squared plus ax plus b is congruent to 0 mod p. And p is a little bit large, like 2-digit large. And then you're probably reluctant to go through all of them, right? And thinking about, is there a better way to do that? If it is degree 3 and higher, we do not have a formula to break this one down, right? Only quadratic works. So what kind of formula are you going to use? Quadratic formula. Quadratic formula, right? That's it. Quadratic formula. So when you go out and do that, let's write down quadratic formula, right? This is prerequisite of this course. Quadratic formula. Let's do it. What's in the denominator? 2a. Now you know a is, no, it's not 2a, it's a 2. Sorry about that. It's a 2 times 1 here, right? Right? Let me go ahead and change that one to a. I apologize, b and c. Then it's 2a, right? Knowing that it's a quadratic, we know a is not congruent to mod p, like in the finite field version. How about 2? P can be 2, right? Then it's a problem. You cannot put 0 in the denominator if p is 2. So this quadratic formula only works for what kind of prime? Not equal to 2. Quadratic formula does not work. And you're curious, well, then what do we do? Well, we have to take care of it separately. But if it is not 2, then it works. Negative b plus minus square root of b squared minus 4ac. Only troubling thing is square root, right? But it is exactly what it is, square root of, you know, whatever it is. In F7, do you know what square root of 2 is in F7? Something you square it, you get 2. Yeah. Yeah, you got it? Yeah. Square root of 2 is? Oh, I see. What is, yeah, okay. So what is the answer? 3? Is that right? Yeah, just 3. It's plus minus 3. If you square that, you get 2 out of it. Because there's no positive and negative notion in a finite field, this has to be the notation. If we rewrite square root of 2, it's usually a positive number in real numbers, right? But not in a finite field. Square root of 2 really means the 2 possibilities. Good? Yeah. So that's the square root what you're talking about. That's the square root. Yeah. Yes. Yeah. No, if you only have 0, 1, 2, 4, right? What is the square root of 3? No. If you square it, I don't get 3. If you square it, there's no 3 in there, right? So square root of 3 is not in the, it's not in there. Where is it? Was it? That's right. It's another one. This is not planned, but I'd like to show you the square root of 3, if that's all right. This is how I introduce imaginary number. This is another one that why you pay for this course. I'm gonna show it to you. All right. Where is the imaginary number? Have you seen imaginary number? You haven't seen imaginary number. I'm gonna give it to you today. Here it is. So idea is the square root of 3, right? Where is the square root of 3? Right? That built upon F7. And here is the secret. All right. If you see 3 and then F7, right? You know what that means. But I'm going to change the shape to 3003. You know what just happened? This matrix is a diagonal element 3, right? So I'm going to use 2, 7 in there, right? So that's 2002. Now I am changing the shape of the finite field with the 7 elements into the matrix like that. So I'm going to call that one G7 like that. And it is a collection of this diagonal matrix where A is coming from F7. Is that right? Now, if I have two matrices A and B from this G7 that has 7 matrices in it, right? What happened if you plus A, if I calculate A plus B? Yeah, what is if it is represented by A00A and that's represented by B00B, that's going to be A plus B00 A plus B, right? Even though we put it into this complicated form, the way the arithmetic works is exactly the same way it works, right? If I multiply A times B, what is it? It's going to be precisely AB there, and 0 there, right? So do you see that this G7, the way the arithmetic add and subtract and multiply and divide, all that, the way it works is precisely the same as F7. And the word is used for isomorphism. The arithmetic defined in G7 is non-difficult, non-different from F7. It's exactly the same, right? With this luxury of 2 more spots, I can create square root 3, right? The rule is the following. I'm going to call matrix M to be 0, D. I'm going to call 3 in there. 3, 1, 0, I think. No, I think it's 1 in there. Hope I'm right. No, that was 0. I'm sorry. And that was 0, yes. All right. So with that one, I'm going to create, I'm going to call R. A plus A is a finite field element. It's A times identity matrix. The I is the identity diagonal matrix. So if you multiply A, you get AA and BB, those things, right? And multiply B to M, and where A and B are coming from, finite field with the 7 elements. All right? Okay. Now, if you add 2 elements from that matrix, from that world, simply it's A1, A2, I plus B1, B2, M, things like that. You can add and multiply and subtract. You do all kinds of arithmetic with the 2x2 matrices, right? Okay. So all I have to show is that M squared, right? Can you go ahead and multiply M squared? Calculate M squared? It's not an exercise, just want you to do it on your own rather than me doing it. Here's a 0, 3 there, 0, 3 there, and 1, 0. Right? Correct? What do you get? You get 3 there, right? Down there, I got 0. How about here? 0, right? Down there, it's 3. Right? So it's a 3 times I. So it works like its square is 3. So this is the birth of square root of 3 added to, if you square it, you get 3 diagonal. That's precisely the way the finite field behaves, right? So this thing is kind of equal to A plus B squared of 3, where A and B are coming from where? Finite field with the 7 elements. So this is how you create square root of 3 and add it in there. What's that? It's a splitting field of x cubed, x squared minus 3. That's right. But I didn't use polynomial. It is actual object you're familiar with. So you can go like this. If you have real numbers, and if you haven't seen imaginary number, it goes like this. A plus B, AI plus B, M, where M is 0, -1, 1, and 0. Then you can calculate M squared is -1 times I, which is -1 and -1. So that one here, where M is like this, This one is behaved just like the complex number. Real number, real number multiplied to m, which behave just like imaginary number. Square is -1. So this 2 by 2 matrix has imaginary number in it. And here's how you actually see it. I give the existence to the world that you understand. And so I prove the existence of imaginary number. This is what I did, right? So I also proved that existence of what? Square root of 3 built on top of what number? Finite field. Yeah. All you have to just is believe. It exists. That's all you have to do. That I explained it, you've seen it, and then you believe. I've seen it. I believe that square root of 3 exists, built on top of the finite field of the 7 elements, right? So let's do it. Can you calculate the 2 plus square root of 3 squared in finite, built on top of finite field of 3? You square it, right? You get 4, correct? So 2 times the square root of 3, right? Plus, what is the square root of 3? That's a 3, right? Correct? Yeah. Well, what about this one in here? The 4, what is this one? It's 4 plus 3. That's a 0, right? That's a 0. That's a 4 root 3. In over finite field. So finite field together with the square root of 3, that's the arithmetic we have created. Make sense? Doesn't make sense at all. But that's the that's the arithmetic we just created. Let's believe there is a square root of 3 built on top of finite field with 7 elements, just like we do the imaginary number. And this is the consequence of the arithmetic. You have it in there. Right? Yeah, that's only Sage. Sage does all that. Sage will take square root of 3 over F7, all that, right? Yeah. This is just amazing world you just entered. This is exactly Alice Wonderland. This is um, coming from there. All right. I want you to use quadratic formula. Because it's mod 5, you can go through 0 to 5, right? But imagine, oh, this guy put in number 6, this one again, you can't inspect it. Just like that, 729 and 1465, right? You know what I mean? So let's actually do more consistent method. I want you to solve the first one using quadratic formula, right? Then break it into simple linear congruence system. That's our exercise number 2 with the 2 parts. Part 1, solve x squared plus 2x plus 2, 0 mod 5, as if it is equation over F5, and find, what was the word? Simple linear, no, simple linear congruence system. All right. Any part that doesn't make sense, don't understand what is instruction? Let's work on this one first. Use quadratic formula. It's okay to have negative number under square root, right? Yeah, you can change the mod 5, whatever you want. So I solved the quadratic equation. Hope it makes sense. Square root underneath it is square root of -4, but it's mod 5, so it's square root of 1. Square root of 1 is plus minus 1, so plus minus 1 there. And 1/2 is a multiplicative inverse of 2, which is 3, right? 1/2 is 3 in F5, so I replace 1/2 with 3 in there. Altogether gives you 2 and 1. Like 100 typos in there, it feels like, but it's not. Yeah, but it should be all time to the same answer. Yeah. Any question? This 1/2 turning 3, that's okay? This is -1, 3 times -1, -3, which is 2 mod 5. Yeah, square root of 1, which is, no. Yeah, that's -1. That's right, -1. So instead of -1, you could use 1 and 4. Gotcha, yeah, yeah. So 1 and 4 is correct. Yeah. Um, because this is a 1 is a 2 times, that should be correct, but that's 1 mod 5. This is the modulo 5 world. Yeah. 3 times 2 is congruent to 1. We treat it as 3 times 2 is 1. Then 1/2 is 3. Yeah, we're treating like that. All right. So to part 2, let's do that together. That's part easy. How do you solve this one? Is that 3? No. What's the answer to this one? X is 2. Yes, 2 is correct. So x is equal to 2. So they have x equals 2 mod 5 and x equals 2 mod 11, right? That's the one case. Another case is x is congruent to 1 mod 5 and x is 2 mod 11. Those are the two separate cases you have to solve to answer that kind of question. Hope that makes sense. Yeah, this is easy. X equals 2 is the answer.